last time we discussed about this quadratic derivation of this GKSL equation, and so we did it in two steps. Primarily, we expanded around t equals to 0, quadratically with up to order delta t, and then we derived this for t equals to 0 here. That everything in the right hand side was this rho t's were rho zeros. So that quadratic step was something called Born approximation, because we are this quadratic expansion means sort of big coupling. Whereas in the second step we took the it to be valid for general times. So that had an inbuilt assumption of the relaxation time of bath being much less than the system time scale. So let's say T reservoir is far less than T system, where this is the system time scale under which in which this density matrix of the system changes substantially or significantly. So all of these things that I have written here, these have S subscript actually, which I have omitted. So all of these are just system quantities after integrating out the part of the reservoir. So what we will do today is derive sort of the same equation, not completely derive I would say, but we'll start from a try to get to a microscopic derivation, and it will not be completely general, because at some point I will shift to a particular example of harmonic oscillators, grand harmonic oscillators, but so that I can also cover an example while deriving it. So let's start. This is typically known as the microscopic derivation that I am going to do. So we always have a Hilbert space of this kind, and my total Hamiltonian is so apart from these two, there is a coupling part which is HSR, I will call it. Say, this is the coupling part, and so from here on, we'll say it is considered, which in most cases are true, is that reservoir is of less concern, and we can specify its properties in terms of in very general terms, in terms of say properties specified in terms of some temperature, chemical potential, density of states, etc. Now let's consider the total density matrix at an arbitrary time as this T I of t. Of course, at time 0, this density matrix, as we assumed, was a product density matrix. That was the density matrix of the total system is always a pure state, but at time 0, that pure state was an unentangled pure state, so there was no coupling between the system and the reservoir. But as time passes on, this HSR introduces coupling, and so this becomes an entangled density matrix, and there is entanglement between system and reservoir that goes with time. So this is my total density operator. And my system density operator I call which is just we have discussed it many times. So the Schrodinger equation for this total density matrix, which is also known as the Liouville-Kornhaim equation, is just this. And again, this H is the total amplitude. And in previous cases, I probably wrote it in terms of minus I in the above thing and nothing in the denominator, but this is very same expression. So this is the full Hamiltonian. And in the interaction picture, now I discussed the Schrodinger picture, interaction picture, and Heisenberg picture in my first lecture. So I'll get to that because in this derivation we will mostly use the interaction picture. And at the towards the end, we will again revert back to Schrodinger picture. So in the interaction picture, this Hamiltonian, if you remember, this transforms to just the HSR part. In the equation of motion in the interaction picture, it will be, say, if I write the interaction picture density matrix as this Finlay expression. Everyday West again over which is everyday, where again this is also in the interaction picture, so any operator. This would have been the interaction picture equation of motion, and if I now use the expansion of this thing, of this kind, we say. In the next step, it will explain. Up to dt prime rho. And where these are distinguished things. Sorry? Criteria is density matrix, total density matrix in the interaction picture. Usual criteria is the total density operator in the Schrodinger picture, and if we transform it to interaction picture, that I have denoted in terms of this criteria. Now, so chi0 we have used here. Let's again for a while. So also remember that at time 0, interaction picture and Schrodinger picture are same. So chi0 is equal to chi t plus 0. And this, let's say we write it as rho 0 and r 0, where r 0 is the path density matrix at time 0 and rho 0, because we are going to focus on the time evolution of this. So let's note this as this r 0, we'll see how this helps us later. And now let us trace out the actual equation was this one. And if we trace out the path from this equation, what we get is simply this. So, but I have also omitted, you can see I have omitted this term here. So, this is a reasonable assumption which is basically saying this case of R case of R is 0. And this means that, let's say, in my HSR I have both system and reservoir operators, but while I am taking the case of a reservoir, I am only focusing on the part of HSR which has to do with the reservoir properties. So whatever, let's say, if my this thing is some SI or RI kind of thing, this RI operators have zero mean in the bath state. This doesn't have any mean. This happens to be a fact that usually holds true, but this doesn't have any physical implication going forward. So, for now, what we will do is focus on this equation and move forward. So, here on, until here we haven't yet made any assumptions, for example, the decoupling or the bond assumption or the second assumption that we have to make, which is the Markovian assumption. None of them we have made yet. So, do those things now. R? R0 is the path density matrix at time, path part of the density matrix at time 0. Okay. For example, I said that path is of less concern and it can be, we can discuss it in terms of the general properties like temperature, chemical potential or density of rate. So now we can treat, let's treat this bath as a thermal bath kind of thing, which is in thermal equilibrium at some particular temperature T. Yeah.
Why is the density matrix evolved according to this stuff?
This because this is just the interaction picture. In any interaction picture, if you remember in the first day.
Yeah, my question is basically what is the difference between density matrix as an operator and other operators which you got?
Oh, density. Any other operators would have just a minus sign.
But then that HSR should have been one particular part of the
No, in the equation of motion, if you just derive the interaction picture, any interaction picture operator evolves like this. You write the equation of motion, it's like I, H I, where total H was H0 plus HI. States evolve in terms of H0. This and density matrix, but remember that density matrix equation of motion is again a Schrodinger equation of motion, but here it is
the states that evolve according to the perturbation and the operators evolve according to the unperturbed dynamic.
Yes, but if you just take the states which are psi r is some to the power I80 t psi s to the power is
What isn't this a state? It will have only one exponential. I have to only source code with one exponential right in front of it.
no, this is you are again confusing it with the Schrodinger state equation because I defined my interaction with just states in this way that in terms of Schrodinger picture states as just u0 t where u0 is e to the power minus I
So why do you have another right after it?
u0 that. This was the definition.
No, I think there's only one factor of u0 in the side interaction.
Here I am not talking about time evolution. This is not time evolution. The very zero time
Definition of interaction.
no, this is my zero time. Let's say any time for any time you can write this. Now I just go back to the first lecture. So if we involve this again, we will refer to the first picture. Ah, yeah, you're right. It was this kind of thing. There was only one. If you do this, but now if you take a I del t of this, what you will get is that because this evolves in terms of the full Hamiltonian, the Schrodinger state of the science, Schrodinger picture state. So if you take identity this side as well, it will act on this and this. So after doing everything, what you will get is it comes out to be this hi times psi r, the equation of motion. So this interaction picture state also evolves in terms of this hi, not h0. And if you now just take the density matrix in terms of this psi i's, but I'm calling this chi tilde t, then it will again be just the hi is equivalent to hsr. As we already discussed, this reservoir can be a large system. Whose state will be approximately unaffected by the evolution. What we will do is we will assume an approximate factorization. And showing deviations up to order first order in this HSR. what I mean is that we'll take this I T as some rho B R0 again, because as I mentioned, this will be largely unaffected, and up to order tilde variations. So this is something which is known as the Born approximation, because we are only considering variations up to order delta r and mostly keeping assuming an approximate factorization of the density matrix at time t also.
Is this the Born approximation?
Yeah.
Is it the same thing that we have as what we have in scattering theory?
It is similar. I mean, there also you can write in terms of some coupling into, you make a series out of those couplings.
Right. Series which also involve propagation, but I don't see
Yes, but yeah, here I am considering keeping this only up to this limit, that decoupling limit is discussed as Born approximation here. So it's not completely same, but yeah, this expansion in terms of coupling parameters that you can do there, we are keeping only up to, let's say, order HSR variations. Again in the interaction picture, but we can start from the Schrodinger picture and also get to this equation. Yeah, this here HSR, keeping HSR of first order terms, with HSR involves has the coupling between the two parts. So keeping no, that I haven't yet assumed. That I when I assume I will say that. So and why this is different from that assumption, that will become clearer. So what this makes only does is, I can write this part as something like rho tilde T prime into R. But remember, this equation is still non-Markovian. So this is my Born approximated equation of motion for the, in the interaction picture, the equation of motion for the rho tilde. But as we discussed, that Markovian means the memory is only from delta t or dt parts. There is not no memory coming from more than that time. But here we have this rho tilde t prime here, which where t prime runs from 0 to t. So the memory of this rho tilde t prime from 0 to t, everything is going in this expression to give me rho tilde dot t. So that memory of the state from 0 to t is inside this right hand side expression. So it is still non-Markovian. This is Born, but still not Markovian. Now there is another way to arrive at this expansion and make sense of it, which is to start from a Schrodinger equation. Say, we make this decoupling assumption not in the interaction picture but in the Schrodinger picture. Means here I had order HSR tilde. If I start from this kind of thing, and so to get to the interaction picture, I will have to take a IH, HS chart in the right hand side, in the second term we will again sandwich it like that and get to just something like order HSR tilde. But before that, in this part, we can actually take this HR thing, go from here to in the right hand side and act on R0, because HR does not act on rho t, which is the system density. And so this acts like actually this, which is t. you look at this part, this is R0, let's say T, or keep a T. Let's say this is not R0 or this is R at T. Get rid of the 0 part. But then what is RT in Heisenberg picture? We use the expression of RT as e to the power minus I over h, which are R0 plus which is basically saying that my RT was only under bath has its own dynamics, but bath does not really dynamically evolve in terms of Hs plus Hr, but in terms of this, if we use that fact, then these factors cancel. This e to the power I over h Hr cancels with this minus I over h Hr, and this factor cancels with this one. So what we are ultimately left of is rho d T into again R0, just R0, but not any time dependent, but the density matrix at time 0. This has an assumption that bar evolves with its own dynamics. Sorry? No, here this thing was there, but this was RT. So here if I use this, if I was using the most general case, if bath was not so big and it was a small thing, then T. Here I would also have HS plus HR into T. No, that what Markov approximation in the microscopic derivation will become because what the other thing that I was saying that bath relaxes and that so on. Again, it has to do with the memory of the thing. How long does bath remember about the system and system remembers about it? But when we are focusing on the system dynamics, the Markovian expansion will mean that whatever I have in the right hand side, this should not have, this T prime should not have memory from 0 to T. So I should be able to replace this rho tilde T prime as rho tilde T. That is Markovian approximation. But even after replacing that, actually, okay, let's get to that a little bit later. But this is the bond approximation after which we can write that expansion.
How it become rho tilde at that?
Sorry,
How it become rho tilde at
the rho tilde is this thing. So this is just no, but this is again writing this as just in terms of the system. So what I can write is rho tilde T is just the interaction picture this as a density matrix of a part. So if you use that, then this is e to the power minus I to the power IHS T into rho 0 into rho T. Sorry, which one? This one? Yeah, this is an exact equation, but again I think here I have used the fact that chi tilde T is chi 0 minus this. I could have also kept further terms I square over h cut square. Weak coupling. So here on we are already said that here on we are sort of keeping first order terms and so on. Order h is yeah. From there onwards I have, but yeah. Again, if you were not keeping this keeping extra terms, you can keep this other terms. But as soon as you make the bond approximation, the other terms will go out. I mean, ignoring anything after order HSR. Or actually here in terms of this, you can think of this as being quadratic in HSR that we have in the equation. That's all until which we focus. So the effect of the interaction between bath and the between system and reservoir of the bath evolution is neglected in the leading order, and this is because we anyway keep only up to quadratic order and any further terms. So the reason this is what I'm saying is I replace this chi tilde t prime here by only rho tilde t prime into RCU because we are not giving this order HSR time term even here because we want to focus only on quadratic order terms here, not because we take this order HSR time term as well, then it will eventually become the total expansion as cubic in the order of it. So the next approximation that I was already sort of said is the Markov approximation, where primarily you basically you don't want the right hand side to have the linearly from 0 to t prime, at least in the rho tilde term. So anywhere else in the other expansions it can have this t prime thing, integrations and so on, but the rho tilde t prime is replaced by rho tilde t. So that makes sure that whatever I have in this side, again we can write the other parts which can be some t time dependent thing which is again start from 0 to t, say t prime, but whatever that is acting on the rho tilde t. So at least in the right hand side, whatever rho tilde we have here, there is no memory about from t prime to 0 to t. It only remembers about automatically about these things. So through this dot, and it will keep this dot. So this replacement is a Markov approximation. But when I discussed this dynamical semi-group properties last day, which was this map followed something like it was this and this associated materials. So what one can show that in this form yet it does not follow all the properties of this dynamical semi-group. And so an extra part is needed which has to do with the fact that even after replacing this rho tilde t prime by rho tilde t, still HSR I am considering from any t prime between 0 to t, and it always starts from 0. But I want to start from somewhere very near t, such that this expansion is sort of valid for all times, but it can start from anywhere near t. Means I want to model this as something like t minus t prime, such that this has a information that how close this each SR tilde is to the actual time when we are trying to measure the operator or the evolution of the operator. So if one changes this rho tilde, not this thing actually, sorry. But t prime to t minus t prime, and then since we are t minus t prime, but we will see that makes this t integration go to infinity. This I will not be able to make sense of right now, but when we see the derivation, this will be clear when we study the expansion. So for now, just treat this as a fact that to satisfy semi-group property, one needs to change this t prime to t minus t prime, and that also here the above limit of the expansion changes from t to 0 to infinity. And this fact that I mentioned, this game can only be done in the limit where T reservoir is far less than T system. That will also become clear when we discuss the example, which we will now get into, which is the damped harmonic oscillator. Before going to the damped harmonic oscillator, maybe I can say a few more things as well. We can do is, let's say, let's consider this HSR, not in the interaction picture, we will get to the interaction picture in a moment. It has something like this, as a sum over I, SI in some basis. This SIs are system operators, and gamma is belong to reservoirs. Then HSR typically will be after mutual evolutions of this and this, we can write in some which is so if you remember what we had here, so we already this as well. But before making the Markov approximation, we had here T prime, here also T prime. So before making the Markov approximation from this kind of HSR, the equation of motion will have something like this. This is a big expression. sort of expanded this whole expansion before doing the Markov approximation. But we have taken trace over the path of reservoir operators, which are sort of these correlation functions, and whatever left is sort of the doctrine about system dynamics. But the information about the path goes into this expansion in terms of these path correlation functions. So, for example, this is nothing but just case of path. And the Markovian expansion of replacing this rho tilde t primes by rho tilde t can be done, let's say, if these correlation functions are proportional to some delta t minus t prime. Then I can, if they have this kind of behavior, then I can replace this, take this Markovian expansion. So I have to study these correlation functions as well and find out the nature of them, and then can we really make this approximation that this becomes delta t minus t prime. If you remember the discussion from last day, in case it is non-Markovian, instead of this being delta function, it will have some memory. It will be some memory kernel function like this, at minus t prime. Let's say in this example, what we will do is we will consider the system Hamiltonian to be consisting of just one harmonic oscillator of frequency omega c, and the reservoir Hamiltonian in this form. And H's are so if we take this sum inside and then we can also write the gamma has inside them on the sum over RJ values. And these are, for now, these are system reservoir couplings, which are small and we say constant. So now we assume that as we already sort of mentioned beforehand, that the reservoir is at thermal equilibrium at temperature T. Then what we can do is we can write down an explicit expression in terms of this RJ dagger oscillators and operators, the thermal density matrix, which for bosonic oscillators in terms of this. However, it turns out that it is not so important to be, as long as we sort of imagine that it is in thermal equilibrium. It's not so important to be bothered about which specific reservoir system that I am talking about. But typically, this kind of many oscillators, many harmonic oscillator reservoir can act as a good reservoir in many physical systems. For example, some leaky cavities kind of system which are dealt linearly in condensed matter, then spontaneous emissions, and also as this reservoir operators or oscillators might represent phonon nodes in a structure. These are just a couple of examples where these can work. If we use this R0 and all of this information,
How are you getting this idea?
R0 is just the thermal density matrix in terms of reprint of C to the power minus beta HR if you write, and just the bosonic part you will get from the Bose instance.
How are you writing this page?
I'm not writing, I'm just assuming this kind of where both system and reservoir operators are present. This can have this kind of couplings. Again, a big expression which is explosive rotor that is there will be operators like this where both SI and SJs are taken as A operators. So, the possibilities are S1 equals to A, S2 equals to A dagger, gamma 1 equals to gamma dagger here, V2 which is just sum over KJ star of J dagger, and gamma 2 is the gamma which is just KJ into RJ, sum over. Cross emission route. So there will be four this kind of terms. One is involving this A. A is like this. One will be like A dagger. Here, everything else as they are. A dagger. This will have plus. Is because the daggers are coupled to RGs which I call numbers. Then there will be one where you consider sort of S1, S2 because I have here SGSI kind of operators as well. So A dagger, then this and this. This term will have minus 2 prime. This will have one gamma and one dagger. Finally, another one which is again involving data dagger. So, is just the expansion of this kind. You can work it out using this S1 equals to A is equals to A dagger. Will be all of these terms where, say, if I try writing out one of these, keeping in mind this as my reservoir density matrix. So if you work out this part, you will see that since there is this RJ dagger, RK dagger thing, and if you work with this R0, both this and there will be another expression where you have both gamma t's, there's no daggers, where you have a trace over R, R0, say RG, RK. Both of these become 0. So these two terms, or rather these four terms, because admission conjugate is also there, these terms become 0. They will not contribute. The only terms contributing are where you have either this or this. So basically where you have case like R0, RG3 dagger, RK, RG dagger RK or RG RK dagger. And in fact, this only contributes this kind of thing, and this contributes something like G plus 1. What are those things? They are this is just the both sides statistic what we will get.
How is this
Which traces?
these traces?
These traces are traces over the reservoir parts that I had everywhere because I have to integrate out the reservoirs. So the reservoir operators which were this RG daggers, RK daggers, those traces I am taking. So if you take this R0, then this kind of trace will never contribute RG RK kind of trace. Only when you have RG dagger RK and even RG dagger RK you find out that they will only contribute when J is equals to K. So that's how this here you would have probably one e power I omega G and one omega K term. So it will in these terms it was like these are the T plus T prime terms. But in the T minus T prime terms, in here also you have this omega G frequencies which are bar frequencies. There you have something like contributing terms will be apart from these things you have e to the power minus omega J T minus T prime, and in another term you have to the power plus I omega J T minus T. So this number is you can think of as being sort of bosonic operation number of an oscillator with frequency Wj in thermal equilibrium at temperature T, which is telling us about the path at thermal equilibrium. next step that one does is basically in this expressions we always had this sum over j's. So we had sum over j's and k's while computing these terms we got rid of because only rj dagger rj kind of terms will continue. We now have only one sum over just j, and that sum over j I will replace it by something like density of states. So when we get this number operators out of it, the path density matrix and so on. So this gives us how many of those path occupation numbers or path levels are occupied and so on. So this path summation over j, I replace it by in terms of my density of states and the frequencies because I also had this e to the power minus I omega t terms which are path frequencies. So them I probably just write in terms of omega, and instead of summing over the j's, I will take this d omega from 0 to infinity. This infinite number of oscillators are present in different frequencies, and g omega is just the density of states. So this g omega d omega gives the number of oscillators with frequencies in the interval w to w plus dw. And since I mentioned these terms that will come out come in terms of this omega j's are always have this t minus t prime. So here again we can introduce a new variable tau, which is just t minus t. So after making these changes, the expression of this thing that we had becomes still I haven't changed this integration. If you remember, I have already sort of this t minus t prime thing I have somehow got, but I haven't yet changed this integration limit to infinity. I had everything rho tildes written in terms of t primes, which I now write as t minus tau. There will be another like dagger A. The same thing. This plus plus where these things that I have written here, this integrations d omega g omegas are inside them. Let's write down one or two. Wherever I had n j's, I have replaced the j terms, I have gotten rid of, and I have introduced omega variable. This is the expression of 7 bar that I got. So now let's revisit the Markov approximation. And where you can really write this kind of things as delta functions, delta. Oh. Yeah, still there will be there is that is why I have introduced a minus sign. So what happens is basically in this expression, when you have this, because one of these terms will have it to the plus omega tau, another term which is sort of gamma dagger that will have into a minus omega tau. And here instead of just this n bar, I will have n bar plus 1 because from the RJ dagger term I got nj bar plus 1 expectation and these terms, what we can do is that this is for the large enough tau. Say if tau is large, then this is highly oscillatory term, which gives rise to sort of very much a lot of oscillations. And these terms, these are the path degrees of freedom, which are in thermal equilibrium, which do not vary rapidly with time. So they are very slowly varying functions. The way one motivates the fact that this will be like a delta function is that this highly oscillating function averages out this slowly varying functions, and so this is known as secular approximation. Or also sometimes people call it rotating wave approximation. So the idea is that this large oscillating terms average out slowly varying terms. Then if I ask that can we get some estimate for the width of this reservoir correlations, it can be, it is going to be a, you can get already some signature that it is going to be something like a delta function because this averages out, but what is the width of the correlations? Then let's assume that this slowly varying function of the consider of this form, just some constant multiplied by omega, then this gamma dagger correlation comes out to this form. Where this is the Bach's relaxation time, which in this case is just h over 3 dt bar, and this is the sine function is trigamma function. And if we look at the real part of this trinomial function and plot it against tau over PR, it turns out that it dies out very quickly and it has the peak near tau equals to 0. This function peaks near tau equals to 0. That's about. And with the width of the order of p.
How we are getting right?
Huh?
How we are getting right?
Just if you use this c omega and perform this integration. So this is just an example that now what happens is, so since it peaks around tau equals to 0, but we are going from 0 to t where t can be any large times as well. But it will always, this path correlation functions will contribute in the most dominant way only near tau equals to 0. Now, these reservoir correlations are integrated against two time dependent terms. One is this rho tilde t minus tau, and another is this e to the power minus I omega c tau. So in situations where the system time scale, you can talk about like this upper limit of t, it's from this ts, is far greater than tr. We can show that we can indeed make this replacement. Because this, again, the path correlation functions will contribute in the dominant value at tau equals to 0. So you can write the t minus tau as just t minus 0 and approximately make this replacement, which was our sort of, we are getting rid of this t prime that we are writing as t minus tau, and now getting rid of the t itself. T prime is just t which doesn't have any integration, we are making tau integration. So that gives us the Markovian equation. Markovian limit. And once we have done that, also another fact is that integrating the reservoir correlations against the oscillating terms like this, there will be one e to the power minus I omega c tau term, another complex conjugator, this will have e to the power plus I omega c tau term. So those, after getting rid of this tau from here and making this integration, they will just give out the omega c part, because everything else is, they do not have any omega dependence. Omega c dependence, no, this also do not have any omega dependence. So this is like d tau e to the power minus I omega c tau terms, which is just like a Fourier transform, which will give you out omega c part. So what we then write is basically this. Well, we have absorbed all this integration kind of things inside here. this alpha is tau remember that we just studied a particular kind of slowly varying function, but in the most general case there is alpha and beta. Beta will be So the next couple of steps are basically extend again because the tau integration is dominated by much shorter time scales. Then we are taking this from 0 to infinity, but it essentially always dominates sort of, you can get that for slowly varying functions, it will always dominate near tau equals to 0. So this tau integration scaling, you can, in fact, whatever is t, as long as ts is far greater than tr, you can replace this t as something like infinity. So it is like far greater than the time scale where the tau scale really gives a dominant contribution. T becomes much greater than tau, and in terms of this t limit, you can replace here. And then everything that is remaining is everything we are doing it in interaction picture. Again, we would revert back to the Schrodinger picture by just doing using the relation between a Schrodinger picture density matrix and interaction picture density matrix, which are valid for arbitrary times. Once we do that, we finally get the expression. So now I have got rid of the tilde, and we just prime. I was dealing with omega c, but I'll say what omega c prime is. So this L that I have written here is just the L that we sort of wrote in terms of the operators laboratory. So L of if an operator acting on rho is defined basically as this. So the rho which is this part of the GKSL equation that we derived the other day. And the primary part, if you focus on this omega c is omega c prime is just omega c plus some delta, and this delta is some integration of this this is apart from that, if you look at this part, just forget about this delta, but if it was omega c into integral a, so this was just my system Hamiltonian that I started with, hs. So it is hs up to this delta shift, which is typically known as the lamp shift. This finally my rho becomes just I hs into rho plus this gamma things will be there, but otherwise again embark in what we discussed. write down. This is a constant number. We indeed get this Lindblad super operator form, and yeah, maybe let's stop here today, and we'll in the next day discuss basically how. So we got everything by doing this perturbative expansion kind of thing, where we use the expansion where we are doing a we are taking weak coupling limit, then we justify it where we can take this rho tilde t minus tau to rho tilde t, because only tau at tau this other parts of the Barth correlation function contributes in a dominating way. In the next day, what we can see is some nice properties of this. For example, what one expects to see, and we will see in the next day, is that if we permit this density matrix to evaluate for a long time, then it will get to a steady state density matrix, which will be again that steady state will be described by temperature which is same as the temperature of the bath that we started with, and so eventually it will be equilibrated with the thermal equilibrium bath. And so although the bath was sort of having its own dynamics and not changing due to this interaction and everything that we assumed in the primary state, what we will see that the system, what we are seeing studying the system evolution, is the system was out of equilibrium, but as time evolves and we go to some t going to infinity limit, we will always find that this t, which is expected, that it also comes into equilibrium with the large bar. And the second thing we will do is we will study a non-quadratic approach and see how this quadratic approach compares with the non-quadratic approach, which is called the quantum Langevin equation. How maybe numerically how they match or they don't, and up to what point they match, those things we will discuss in the next. Okay. Is there any further question?